Okay, welcome to the Introduction to High Performance Computing lecture. The main goals for this lecture are to first introduce you to some of the terminology and the benefits of using high performance computing. And HPC is almost by definition a remote computing system, meaning it's not local, it's not your desktop or your laptop. So how do we get into and access and do computing on remote high performance computing resources? And to do that, the second main goal is to make sure that you get login credentials. It's important that you do that as soon as possible, as I said in the introduction to this module, because after you get your credentials, you have to give those to me, and in the PowerPoint, I'll show you how to do that so that I and the TAs can get you assigned to our allocation, because you have to be assigned to the allocation in order to start running compute jobs. Okay, so let me switch over to share my screen. So this is the Canvas page, the video and media for Module 3. You're watching this video. Hopefully you've already downloaded the Intro to HPC PowerPoint. It's got some links that will be handy to get to the account setup pages for Access and the Pittsburgh Supercomputing Center, which I'll talk more about in a minute. They're also here on this page, just so the links are in as many places as possible to make your life a little easier. And with that, let me jump to PowerPoint. So like I said, high performance computing, I'll say HPC all the time. What is it? It is remote hardware, sometimes called supercomputers. When people talk about cloud computing, they are talking about computing on some kind of HPC. Why use them? In case it's not obvious, more computing power. They have many, many more cores, processing units than your desktop or laptop machine has. Depending on the machine, they may have much more memory. So RAM is random access memory. We'll talk a little bit later about why cores and RAM are important for certain kinds of jobs. And then also more storage. I put infinite in quotes there because the cost of hard drive capacity, and now we're moving to solid state disk capacity, is so low now that there is essentially unlimited storage space to house data sets. And especially when we start talking about very large data sets that you can get with some sequencing projects, you need all of those cores and all of that RAM in order to really do the analysis that you want to do. High performance computing power is measured in something called flops, floating point operations per second. This is how flops are calculated. I won't ask you to ever actually do a calculation, but it's kind of interesting to sort of see the levels of architecture that are involved in determining sort of the power and the processing capacity of an HPC system. In the next couple slides, I'll talk about what are racks, nodes, sockets, etc. But all of those things multiply to give you the number of compute operations that can be done per second. Just to give you sort of a real world idea for what modern computers are capable of, your desktop or laptop computer is probably measured in the giga to maybe low teraflops range. I think the new MacBook Pro, I forget, M2 or M3 chip, there's going to be an M4 chip if it's not already out, Those are maybe up to 10 teraflops. But if we just think about 1 gigaflop for a second, so the low end of a modern personal computer, that's capable of performing 1 billion floating point operations per second. So to match that, what probably feels like a dinosaur computer right now, to match what that can do in 1 second, you would have to do a calculation every second for 31 and a half years. So obviously incredible compute power, even in your desktop computer. But that's still not enough when we talk about some of these big data projects. I've put a couple links here if you're interested in like what do the modern HPCs or the top 500 is this website. What can they do? And just to give you an idea, if you follow those links, you can navigate to a page like this. This is the list. So the most recent update was from June 2024. And you can see Frontier, which started in 2022. It's still the fastest, but it has almost 8.7 million cores. So we'll talk about how cores translate into processors and stuff like that in a second. But it can do the peak flops on Frontier are 1.7 exaflops. So that's like 1,000,000 times faster than your local computer. So think about, you had to do 31 years for a giga. That's 1,000,000,000 times faster than a giga. So like 31 billion years, something like that, to do what Frontier can do in 1 second if you were using all its resources at maximum efficiency. So crazy levels of compute power. To use remote hardware, because it's remote, you have to have some way to log into that machine. So typically, at least traditionally, we used the terminal in the SSH command, which stands for Secure Shell, and you would type in your username and password, and it would connect you via that terminal to the remote system. It's increasingly common that interface is mediated by a web browser. So Bridges 2, which is the system we're going to use, has a browser-based method for connection. Later in this lecture, I'll show you how to do both, the SSH method and how to get there from the browser-based method. Browser-based methods are just awesome for those of us like me who grew up only being able to SSH. You'll see there are lots of cool features with the browser-based interface. In the US, the federal government, so mainly it flows through the National Science Foundation. They sponsor advanced computing infrastructure nationwide for research and education. And the program that governs that is called Access. This has only been around for a few years, and I cannot imagine a worse sort of acronym for this program because you can't Google it. So it stands for Advanced Cyber Infrastructure Coordination, Ecosystem Services, and Support. If you go to the Access homepage, you'll get to something like this where you can get started. But maybe you can imagine if the federal government is millions, maybe billions at this point, of dollars in support for these giant computing systems, there has to be some governance, like who gets access, how much access, things like that. And so that starts to get into why you need credentials to be able to do compute jobs on these systems. So step one for you this is an action item, is to create an Access account. So if you click on this button, it will take you to this page. Well, not that page. Click it and actually do this. Right. So takes you here, and then you'll click to create an account. So just follow the instructions. You'll have to set up multi-factor authentication. That's probably the #1 place where students get hung up. But it shouldn't be any harder than logging in to UTA. And in fact, you may be able to use your UTA credentials. One of the challenging things about teaching intro to high performance computing is that the credentialing systems change all the time. And I think Access, at least it was on their schedule of things to get operational this year, was to have institutional login. So you might be able to use your UTA login. Unfortunately, I can't see or help with most credentialing and login problems. If you run into a problem, you will have to contact the help desk at Access. They're usually fairly responsive. I have great success, not on the weekends, but they should be able to help you, and this shouldn't be difficult. You're just setting up a user account. So that's the first credential that you need in order to get onto Bridges. You have to have an Access account. Okay, so here I'm saying stop. After you've gone ahead and gotten your Access login, I need you to go to this Google form. So if you click on that, it will bring you to this page. And you'll pick your section, whether you're in the in-person section or the online section, and then your name, UTA ID, UTA email address, and then finally, and most importantly, the Access username. I need your Access username associated with your UTA ID so that I can add you to the allocation in Access. That's what's going to allow you to run the Pew jobs. Okay, so like I said, whoops, you can also access that form from the at a glance page. So the very first page for this module has another link to that Google form. So hopefully you now, if you're advancing the slide, you have an Access username and you've gone and put that Access username into that Google form. So back to the overview of what's HPC and why do we use them. They are distributed. So many times data and file storage may reside in a different place than the actual computing and memory hardware. You may not even know where your data is physically being stored. What that means is that the compute nodes and the storage nodes are connected by very high speed internet. Looking at the internet backbone for the US, right? So what do we mean by sort of cyber infrastructure? You can see the red lines in particular. These are the super high speed connects. So this is a few years old now, so this is constantly being upgraded as well. The pathway isn't necessarily, these connects are still, I think, all the same, but you can see that Pittsburgh is connected to our area here in Dallas by the fastest internet connections in the world, really. So that's important when we want to move big data and things like that. We won't have to do that too much in this class, just because it's not necessarily, I can put it there and share it with you. But this gives you an idea when we talk about distributed systems. You might have data that's not being housed in Pittsburgh, even though you're doing compute in Pittsburgh. Now, in our case, we're going to have data on storage on machines called Oceans. That's just what Pittsburgh called their machine. And Bridges 2 is the actual compute resources. And those are in separate racks. We'll talk about what racks are in a minute. The right-hand side of this slide just gives you an idea for the catalog of resources that are under access governance. And it's kind of neat because, actually, let me switch over to the actual site. I can show you, right? There are lots of resources under access's purview, right? We're going to use Bridges 2, and you can see there are multiple different options here, right? So I just talked about how PSC Ocean is the storage resource that we're going to use, and Bridges 2 regular memory. We'll talk about regular memory, GPU Extreme in a second. But those are just a few of the resources under their purview. TAC, which is the Texas Advanced Computing Center, is the one in Austin. And we could use that, and we'll talk about reasons why you pick one versus the other also in a minute. But this just gives you an idea, and the updates to this site are great because on demand is the browser-based interface I was talking about. So you can say, select, you only want to know which resources have a browser-based interface. Well, you can see the list is smaller, but it is growing. TAC is not on there, unfortunately. Let's go back. So Access is the umbrella organization. All of those different resources were things that they manage access to. So that's your access username, your access account gets you the opportunity to use any of those resources. When it comes time to actually use one of those resources, so in our example, we're going to use the Bridges 2 HPC that is governed by the Pittsburgh Supercomputing Center. Each of the resource providers, in this case, Pittsburgh, has their own requirements for login. So you need to follow this link. The second step in getting you access to computing on Bridges is you have to get a Pittsburgh credential. So it's getting closer to where the resource providers and access are totally on the same page. You should, this is hard for me to double check because I have legacy access to all this stuff, but I think your access username and account are going to still work at Pittsburgh, but Pittsburgh is going to require you to set up a unique password. So when you go to the Pittsburgh user guide, switch back over here, right? Go to the top. And you read through this, it'll get to, do you have an account on PSC already? No. If you don't have one, then go to the web-based PSC password change utility. And don't let that be confusing in terms of, there's not an account creation link. There's a password change link. And that's going to take you to this. And I think this is badly worded, but begin password reset. You don't have a password yet, so you'll go there. This username is your access username and the email that you signed up your access account with. You submit that, they'll send you an email that then has a link for you to go and set up your Pittsburgh password. Doing that process, setting up that Pittsburgh password, is what's ultimately going to get you access to the next step of getting into Bridges 2. And again, just like with access, this is something that I can't really help with because it's between you and Pittsburgh, and that's intentional because this is a security issue. Um, they're only going to give you information and help the person who is trying to get set up. So if you run into an issue with Pittsburgh's password, you have to use Pittsburgh's help desk. Okay. So hopefully you've completed that. Next step, I've already been throwing around a bunch of terms for what goes into an HPC, but they really do have complex hardware configurations. Processors, memory, storage configurations are all tailored to different computational challenges. So what that means in terms of picking which high performance computing resource you want to use out of the list of access resources, for example, it means you have to have some familiarity with your computational needs. Ideally, you want to align the project with the resource that has the best infrastructure for you. That goes along with, knowing how many nodes and cores. Can you make the job be parallel, or break the problem into lots of small subsets and then run them all at the same time? That's something that where you can take up more cores versus something where every computation depends on the previous one. That is more serial, not parallel. And then all of the resources have time limits. And what I mean by time limits is you will submit a job and you can only reserve those resources for a set amount of time, like 48 hours, for example, is usually the most that you can reserve. One of the, or I should say maybe two of the hardware configurations that we're going to be most familiar with are the login nodes, which are for administrative and housekeeping functions. When you sign in, you join a login node. And you can do file management, software installation, and all that kind of stuff on a login node, but you don't do computing jobs on the login nodes because that's where everybody is using that node. When it comes time to actually do say we're going to do blast or alignment, actually run a job, you're going to send that job to a compute node and it's going to run the analysis for you. So which HPC do you use, right? That issue of, they have different complex hardware configurations and you need to know something about which one to pick. In principle, you're you're picking the resource that best fits your job. So examples here that are pretty common in biology. If you're going to do de novo genome or transcriptome assembly, that's a situation where you have millions and millions of short reads where the efficiency or the speed that that job completes is going to be determined by how many of those reads can it hold in memory, because it's doing all versus all comparison to see which ones match up with each other. So the more RAM you have available, the more reads you can simultaneously store in memory, the faster that job will be. That's in contrast to something like phylogenetic inference, where you're trying to build trees. That's typically compute limited. You want to test the fit of the data to many, many, many different tree topologies or sort of phylogenetic branching structures. So you can imagine you've got one set of data and a sort of, thousands, hundreds of thousands of potential tree topologies. You can test the data on each one of those on separately on an independent core. That's a highly parallelized problem, right? So if you have thousands of cores, you can test one tree on every core and be done in a second. Whereas if you had to do them one at a time, it would take a really long time potentially to run that in a more serial fashion. So that's just one example of sort of the extremes of the spectrum where you might be either memory limited or compute limited. And knowing something about how your job works helps you pick which high performance computing system to run on. What happens in practice is that people choose the machine that has the software they need available. Now, for our final exam projects, we're actually going to install some software because it's sort of brand new software and it's not pre-installed on any HPC. But you just kind of have to trust that I'm picking the right one in this case. Installing software on an HPC is not always easy. In fact, it's usually really hard, and they have dedicated teams to help people install and optimize their software for the HPC environment. Because you can imagine, especially if a job has to work on multiple nodes. I know nodes is not, what a node is maybe not clear yet, but think of it at like running across multiple computers at the same time. Those computers have to be able to talk to each other really fast. Okay. So that poses a problem for software that was designed to run on, say, a traditional desktop or a laptop where it's really just one computer. So this is what I mean by off-the-shelf software is usually not able to run or take advantage of the HPC environment. So if you can't parallelize your job or you can't run it across multiple nodes, a lot of times the only benefit of not doing it on your local machine is that your local machine isn't sort of getting overworked and you can do other things on your local machine while it runs someplace else. Providers in the access system like TAC, the Texas Advanced Computing Center, and the Pittsburgh group, they have somewhat tailored the software availability to the appropriate resources. So this issue of, in practice, people choose the machine that has the software already on it. Well, the people who run those machines only really put the software on there that is best optimized to run on their infrastructure. So these two in practice aren't all that far apart. Even if you don't know a lot about your compute problem, is it more memory or is it more compute limited? The fact that the software is already installed on that HPC system may tell you that it's okay, or at least the governance of that local HPC thinks it's okay or semi-optimal for you to run that kind of computing job on their resources. Okay. Okay, so hardware terminology. I've already been throwing these around. So what's a rack? These are pictures of two racks, right? So there's a rack here. Each of these racks is holding multiple units. So this is a zoom in on a one unit, or sometimes they're called blades. This is the physical structure that contains one or more nodes. You can see all these yellow wires. This is the cabling that allows the different nodes to talk to each other really fast. So what's a node? So if you were to pull out one of the units, you could then pull out a subsystem of that, the node. This is the basic unit of computing. So you can think of this like your single desktop or laptop computer. And they're just happen to be connected by this super fast networking. When lots of nodes are connected in this way, we call it a cluster. You could do this with desktop computers if you have the right sort of networking card installed, and make your own cluster. People do this for gaming and things like that. HPC nodes sort of introduce complexity on multiple levels because not all nodes are created equal. We talked about how HPCs are tailored to different kinds of computing challenges. Well, that goes all the way down to the node and then even the subparts of the node. So CPU nodes, let me actually go ahead and put all these definitions out here because I know I'm throwing lots of acronyms out there as well. Right, CPUs are the central processing unit. This is what runs your local desktop or your laptop computer. Um, so these are similar to what you would find in a desktop or a laptop, except that oftentimes in HPC nodes, you'll have more than one socket. So probably your laptop or your desktop only has one CPU. Many, if not most, HPC nodes will have at least two CPUs. There are also GPU or graphical processing units. This is a traditional CPU node, so I didn't put a picture of a GPU node in. They look a little bit different. But the difference between a CPU and a GPU is the number of cores. CPUs tend to be more powerful per core, faster per core, but GPUs have thousands more cores. Sort of getting ahead of myself there, because the next picture is, what's a CPU? But then just to be clear, the other parts of this node, all of this is the RAM. So these are little cards that have RAM chips on them. So that's the memory component. And then under this housing, you would find things like the power supply, just the PSU, hard disks or solid state drives. That's the storage component. Another kind of node is the storage node, and that would be dominated by disk drives or solid state drives. So most of this card or this unit, this node would be taken up by the actual storage devices with minimal CPU and memory to just sort of do the file system input and output and sort of govern that. And then if you were to zoom in on one of these CPUs, you would see something like this. So modern CPUs all have multiple cores. This example, I forget, it's 32 core maybe. But right, what I have circled in white is an individual core. This whole chip, which is underneath that heat sink, you can imagine maybe, or maybe not, that the electricity flowing through here to do all those computations puts out a lot of heat. And so one of the uh, constraints actually on speed is how hot these things get. And so usually you can't see this part because it's covered up by a giant heat sink to try to dissipate the heat. Lots of bad things happen when CPUs get too hot. The best of which is just that the program crashes. Like I said a minute ago, GPUs have more complex architectures. If this has 30 cores, a GPU infrastructure architecture could have thousands of cores. On the next page, when we talk about bridges, specific nodes, I'll just give you an idea for what I mean by that. Most modern cores can also perform multiple threads per cycle. So a cycle is like one round of doing compute. So some of them can actually do multiple computes per cycle. And then the last sort of element, remember that calculation of flops or the ultimate power of an HPC. is how many cycles do they do per second, or the frequency. That sometimes is equated with speed of a core. Like how fast is it? How many computes can it do per second? So you can see the infrastructure gets pretty complicated. Hopefully, this gives you an overview. When I keep throwing around hardware terms, you can go back to the slide and sort of at least get localized in terms of what scale are we talking about. When we talk later about submitting jobs, how many cores are we going to request? Well, if we have to reserve one node and that node has two CPUs with 64 cores on each uh, processor, that means there are 128 potential cores on the node that we reserved. So we could say we want to run our job on 128 cores. That's the kind of level of specificity that when you reserve resources and submit a job to run, you'll have to tell the system, and that way it knows how to allocate. Because again, remember, these are systems that have many, many users. And so you have to sort of get in line, reserve a resource, or a node or multiple nodes, and then run the job. And so it needs to block out or reserve that resource isolated from everybody else before it can run your job. Okay, so bridges 2 specifically, three main types of nodes. There's a regular memory node. Won't just walk through all of these. An extreme memory node, right? Talking about compute versus memory limited jobs. And then the GPU nodes. So I talked about having lots of cores. There are 8 NVIDIA nodes on bridges 2 that have a total of almost 41,000 cores, compared to, less than 10,000 CPU cores. Obviously, great if you can parallelize your job and run lots of little jobs. The difference between CUDA cores and tensor cores, not super important to know. These are sort of like the ones that govern what's going on when you've got this many small cores going on, and you need something to regulate how data is being distributed across those cores. At least that's one way to think about it. Those GPU nodes also have some CPUs on them, again, to help govern at a higher level where the data and how the data is being distributed across all of those smaller cores. The individual cores on a GPU node are not as powerful as the sort of standard CPU that is in your desktop or your laptop. And again, the difference being, is it a serial job where you need the output from one step to inform the next step, in which case you need it, like each individual step, to go as fast as it can so that it can feed into the next one. That's a CPU environment, CPU type challenge. Whereas if you can distribute the challenge or the problem into lots and lots of little pieces that can be analyzed at the same time, then GPUs, even though the individual cores are much weaker and slower, you've maybe 100 times more cores, or at least thousands of times more cores. And so it ends up being faster in terms of the total job. And so GPU nodes, NVIDIA, that's the company building the systems that generate the ChatGPT and things like that, right? Those large language models are essentially building the correlation between every word that's ever been written down. And you can imagine, like, that's a hugely parallel job. Like how often does and get used right next to the, for example? You can imagine doing that on every possible combination of words. Um, that's where you can parallelize that job, and GPU architectures have sort of revolutionized the AI environment. Okay, last step here in terms of goals is you have to set up that password for PSC. Already talked about this a little bit, showed you. This is a direct link to, whoops, not sure if that link is going to work. Okay, that bottom link was intended to take you. This is another thing about trying to link to credentialing sites is that they're meant to be secure so that people can't hack them. Yeah, I don't, so that link doesn't work. But you saw how to get there. I navigated to it earlier. You can open that hyperlink, which will take you to the user guide, right? And then this is the link that I was trying to navigate um, to set up your PSC password. Try to fix that, repost the PowerPoint. So if that works for you, it means that I was able to get it fixed. Otherwise, that link might not be there. Okay, so once you've got your PSC password set up, even before I put you into Access, you should be able to SSH into Bridges 2 because you're not actually going to be running a job, you're just logging in. So I can open my terminal here and I'll do SSH and my username is jpdame at bridges2.psc.edu. Okay, and then it'll ask me for my password. Maybe I remember it. Okay, and so you can see it's telling me that I connected to Bridges 2. It's telling me about the resources that I have available. You won't see this because you're not added to the allocation yet. But you can also see that my prompt changed. So now it says I'm jpdammit at Bridges2 login 014. So that's the actual login node that I am logged into. And you can see that changed from, let me blow this up a little bit. Up here, right, Artemis is the name of my laptop. So that's where I was. When I logged in, I became jpdammit at Bridges 2. So this terminal is really a window into a machine I am now computing, or at least logged into, this login node in Pittsburgh. So my laptop has gone over the internet, did the SSH, and now I'm on this login node. So you should see something like this, right? The numbers all change because our allocation changes. We have much more resource right now because our project is all going to run on Bridges this semester. The second way that you can get there is to use on demand. So this is the browser-based method that I was talking about, that instead of doing SSH to get in, oh, Hmm. Oh, that was really strange. So you saw it showed me an error. Then I clicked the on-demand thing again, and it didn't take me back to the login screen. It took me to the home page. So if you don't get the error message that just popped up for me, you should show up on this on-demand login page. So that will go to some. It may pop up a image like this. This is another thing that keeps changing. Uh, but from that site, you can take clusters. You can go to shell access. You can also now use this if you make it to that home page. It's going to ask for your password again. It's the same one. This is your Bridges password. And now this is just like my terminal, right? So I basically never use my terminal to log into Bridges anymore because I can get to on demand. And if I click home directory here, for example, there's another way to get there. You can go files, home directory, but um, this is drag and drop. So this is like a graphical user interface to the Bridges 2 file system that's in your home directory at first. You can see the path to that directory up there. We'll talk more about navigating once you're into Bridges 2 when we get into Module 4. But for now, this is the end of where you need to be for today. Whoops. So, right. So this is what I was just showing you. Log in from on demand. If you can get there, you're great. Last bit about using high performance computing systems is that to actually do compute jobs, which at that point we were just on the login node. Don't do computing on login nodes. Well, I'll probably beat that horse to death when we start running jobs because people accidentally run them on login and we nodes, and we get in trouble for that. But you'll have to do a job script, which is all those things that I was talking about earlier about requesting a node or a certain number of cores that tells Bridges 2 what resources you need. The job queuing software, sort of the thing that keeps people's jobs in line and does the reservation and then sends it to the nodes, the compute nodes, is called Slurm. Um, we'll talk lots more about that when we get to start actually running jobs. Just one other note there that when you ask to reserve a lot of resource for a long time, you should expect to wait in the queue for a long time. But again, when we get to running our jobs, all of that will probably make even more sense. Time on the HPC is currency. So when we talk about an allocation, for this course, I had to submit an application to get time on the HPC. Every job we run eats into that time. And there's a finite amount before we have to go back or before I have to go back and say, we need more time. And then they can deny it depending on the use of their systems. And if there's not enough time for the number of requests that they're getting. So all that to say, you can't just go run things on this on your own. You have to be on this course's allocation. And so to do that, you have to go submit your username to that Google Sheet so that we can add you to the course allocation. Okay. Another note, go fill that out. you can't move on to module 4, or you won't be able to do anything on module 4 until that happens. This is what I see on the back end, right? I can't help you get your account information. I just need the information from that Google form so that I can add users to the resources. So you have an example here, right? This is what I'm going to do for each one of you. And that is to add you to say, yeah, it's okay that Jiaju is going to run jobs on bridges too. So make sure you get that done. So that way you can be ready to go for module 4. Right, that's it for introduction to HPC. Good luck with the rest of the Roslyn problems. Remember, the last Roslyn problems are due Thursday, and the midterm is also on Thursday.